Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1. Find the divergence of the vector field. F equals e to the xyz, secant of xyz, arctangent xyz squared. Boy, they really love throwing xyz's around. Now, this is the fun one. I like divergence. It's fairly straightforward. Okay, so what do we do? What do we do? Well, divergence, that's the one that involves the del operator combined with the dot product. So we would say divergence of f, that's our del dot f, and that means we're taking our partial derivatives, in this case, partial x, partial y, partial z, dot our function. So we'll just copy this down. E to the xyz, comma, secant xyz, comma, arctangent of xyz squared. All right, and the dot product works. We do it entry by entry and add up the results. And so remember, for divergence, we're going to start with a vector value function. We're going to end with what we call a scalar function. So the end result better not be a vector. So partial x of e to the x, y, z. All right, not comma, plus partial y, secant of x, y, z, plus partial z, arctangent x, y, z squared. Now we just have to do these partial derivatives. And divergence has relatively few partial derivatives, so that'll make it go pretty quick. Gonna just make sure we know our chain rules. Derivative of e to the something, that's e to the something, so xyz, times the derivative of the inside. What's the derivative of xyz with respect to x? It is yz. All right, next up, derivative of secant. Well, secant tangent. Leave the inside alone. So it's secant xyz, tangent of xyz, and now multiply by the derivative of the inside. What's the derivative of xyz with respect to y? xz. Cool. Now arctangent. Arctangent. Derivative of arctangent is pretty cool. It's 1 over 1 plus whatever's on the inside, xyz squared, quantity squared, times the derivative of the inside. Now the derivative of the inside with respect to z. xy is a constant, derivative of z squared will be 2z, so that gives us 2xyz. All right, and now what do? We box our answer. We're done. What? It can be that fast? Yes, it can. They won't all be this fast, so don't get used to it. But especially, divergence is just like, hey, it's like we're asking you more or less, take this derivative. And it's a particular form of derivative that's associated with vector valued functions. Nice. What a great start. All right, let's keep going. Number 2. Find the curl of the vector field. F equals x squared y plus 3xzi plus e to the y plus z minus 3x squared zj plus xy cubed minus 17zk. Okay, so that's great. Now, by the way, they might give you a vector in 2 different ways. Here we give it in the form of ijk. We should note this is the same as f is equal to x squared y plus 3xz comma e to the y plus z minus 3x squared z, comma, xy cubed minus 17z. So if you're given it to it in one form and you prefer the other, just put it in the other form. Do what works for you, because that's what we want. We want you to succeed. All right, now how do we begin? Well, we say, what is curl? That we know the answer for. We say if we're trying to find the curl of something, well, there's the formula. Curl of a vector field, f, that's equal to del cross f. Well, so we're doing a cross product. Well, in this cross product, kind of unusual when you look at it. You have I, j, k. I like to give myself lots of room because we're going to write a lot of stuff in that third row. Now, here, del, that's our partial x, partial y, partial z. Now, the last row, that's the pieces of this function. X squared y plus 3xz, e to the y plus z minus 3x squared z, and xy cubed minus 17z. All right. Good. Okay, so how do we take this determinant? Very carefully. Well, we do diagonals. So we're going to have our down diagonals, right, where we wrap around. And let's go through and work out what those are. Well, we have partial y of xy cubed minus 17z. Well, there's no y in that 17z term. And the derivative with respect to y of y cubed is 3y squared. So that's going to give us a 3xy squared I. Right? That's our first diagonal. J partial z of x squared y plus 3xz. So take the derivative of this with respect to z. Well, no z there. Derivative of 3xz with respect to z, 3x. So we're going to have a plus 3x j. Then finally k, partial x of, and it's e to the y plus z, no x, and then here, derivative of minus 3x squared z with respect to x, well, that's minus 6xz k. All right, now we're halfway through. But we have to do the other diagonals, right? You've got some downward diagonals. We also have upward diagonals. And so here, we've got to remember we have some other ones coming around as well. So, for our first diagonal, we have what? The k, partial y, and x squared y plus 3xz. So it's derivative with respect to y of x squared y plus 3xz. Say, okay, well, there's no y term there. And here, derivative of x squared y with respect to y, x squared. And because it's going up, a minus x squared, and so minus k, right? The minus because of we're going up. Next one, I, partial z of e to the y plus z minus 3x squared z. Okay, well, that goes away. Derivative of z is 1 when we take derivative with respect to z. And derivative of 3x squared z is minus 3x squared, right? So we're going to, again, subtract, parenthesis, 1 minus 3x squared, and that's I. Okay, finally, our last diagonal. Okay, so xy cubed, partial x, j. So we're in j, derivative with respect to x of xy cubed. Well, that'll be y cubed. So minus y cubed j. So that's our determinant. And now we just group things together. So we have 3xy squared minus 1 plus 3x squared, and that's I, plus 3x minus y cubed j, and minus and minus, so we can just pull out a minus. 6xz plus x squared k. And we're done. Now, you might ask, can we check our work? There is a couple things you can do to check your work. It's not a perfect check, but it's not a bad check. And it uses the following fact. If you take the divergence of a curl, and it doesn't matter what you start with, you should always end up with 0. So the thing is, divergence is really quick. So let's do our divergence. What do we get? Well, we take the derivative of the first term with respect to x, 3y squared plus 6x. Now take the derivative of the second term with respect to y, and what do we get? Well, that's 0. That's minus 3y squared. Now take the derivative of the last term with respect to z. What do you get? You get a minus 6x, and lo and behold, that was 0, so that's good. That's a good sanity check. Does it mean you absolutely got it right? No, but it's a sign that we probably did. And so in other words, if it weren't 0, we definitely got it wrong. Okay, so that's good. Woohoo! Now, pause for a second. Look at these pieces. Do you notice anything missing? Because I think this is good to point out. What's missing? Well, there's nothing that looks like an e to the y. There's also nothing that looks like a 17. Now, do you notice what's going on with those terms? This e to the y is in the middle column, and that's where you're taking a derivative with respect to y. So the only time you have e to the y involved is with derivatives not with respect to y. Similar, this 17z, that's in this last column, right underneath the derivative with respect to z. So the derivatives that you're taking are not with respect to z. So it turns out that for the curl, if you have functions with respect to x in the first, and only x, functions only with respect to x in the first piece, functions only with respect to y in the second piece, or functions only with respect to z in the third piece, they all go away. And you'll see this happen later on, because we're going to do stuff with the curl. It's not just oh, here's a fun toy. It actually has some interesting meaning. And when you see like really terrible functions, you say, oh, wait a second. Those would vanish if I weren't taking a derivative with respect to x in the first, or so forth and so on. Oftentimes, when you see something terrible, it's a clue you're supposed to make those things go away. And but that's a story for another day, and it's a wonderful story that we have to look forward to. Just like we have more problems to look forward to. Yes! Let's keep going. Number 3. Find the mass m of a thin wire that lies along this curve. R of t is 7, 9 minus 6t, 8t, and t goes from 0 to 2 pi if its density is given by, density is 3, 4 plus sine of 6t. Okay, so we have this wire sitting somewhere in 3-dimensional space. And we say, all right, well, how do you find mass? Well, the good news is the formula for mass is very consistent. And so we say, hey, I know how to find mass. What you do is you add up along the curve. So you can think of a wire, a thin piece of wire, is being traced by a curve. So C for curve. And then its density and ds. Now, what do we do? Well, we're going to translate everything in terms of t. Okay, so we're going to say, what's our density in terms of t? Good news, we know that. What are our bounds in terms of t? Good news, we know that. And then what is this in terms of t? Okay, we got to talk about that. So, as a reminder, we got to figure out what is ds. So, there's a formula for that. Who would have thought? Well, we all would have thought. So ds is the square root of dx squared plus dy squared plus dz squared. Really, I should say x prime squared, y prime squared, z prime squared. And so you're right. I should say that. Let me cross this off. I want to say it that way. Square root of x prime of t squared, y prime of t squared, and z prime of t squared dt. And we have x of t, y of t, z of t. So what is x prime of t? 0. So we square that. What's y prime? Negative 6. Square that. What's z prime? 8. Square that. Well, that becomes 36 plus 64 is 100. Square root of 100 is 10. All right. Well, okay, so it turns out when you go in a straight line, your ds is some multiple of dt. I should say if you go in a straight line at a constant pace. You can have crazy things happen, but, that's not for now. So for us, we put everything now in terms of t. 0 to 2 pi. 3 times 4 plus sine of 6t times 10 dt, right? It's our bounds, our density, our ds. Well, okay, we can certainly pull the 30 out in front if we wanted to, or not. Okay, let's see, what can we do? Well, let's take 3 and 4 and 10. What would that be? Well, that would be, I'm going to just distribute this through. That would be 120 plus 30 sine 6t. And we can integrate. And that would give us 120t. Yes. And now the integral of sine is negative cosine. So negative cosine 6t. But notice the 6 here. So you got to compensate for that 6. How do you do it? You divide by 6. So that becomes, there's a 5 in front. And now we're going to plug in from 0 up to 2 pi. Okay, so 120 times 2 pi makes 240 pi. Subtract 5 and cosine of 12 pi. Well, that's just like we've gone around the circle a bunch of times, but we're back to the beginning. It's the same as cosine of 0, which is 1. All right, then we're going to subtract 0 minus 5 times cosine of 0. Well, that's also minus 5. And those terms cancel, so we're left with 240 pi. Nice. It's easy as 240 pi, right? Okay, yeah, not too surprising. Very straightforward. When it comes to massive wires, we were really lucky. We got a very nice ds to work with. And there you go. It's wonderful. Good. Well, let's keep moving. Number 4. Find values of b and c so that this f, y cubed plus 4cxc cubed, y squared bx plus 3c z squared, and 2zy cubed plus 6cx squared z squared is a gradient field. Okay, so let's remind ourselves. What does it mean when it says, hey, this is a gradient field? Well, what that tells us is it tells us the following, that capital F is equal to gradient of f. So, in other words, this is equal to fx, fy, fz for some function f. Now, this suggests 2 strategies that can work. And let's go ahead and do both of them, right? Double the fun. Ah, beautiful. We get to double our fun? Yes. Okay, so here, strategy number 1 is attempt to find f, and we say, okay, what does this say about b and c? Or we could say, instead of what does this say, what does this force for b and c? All right, so that's strategy number 1. Strategy number 2, well, there's this really cool fact that says if you are a gradient, field, which is what it says, then the curl of a gradient field always has to be 0. So we say, let's take the curl of f and set it equal to 0. And again, what does this force for B and C? So both of these will work. And all right, let's go through. Let's try strategy number 1. And I should say strategy number 2 only works if you understand curl of a gradient is equal to 0. And so this is not true for every field. It's only true for gradient fields. So, okay, here we go. Here we go. What we have is we're going with strategy 1. We need to find f. And what we're going to do is we say, well, you know, lucky us, very lucky for us, we have things which are almost f, or just partial derivatives. So what we can do is say, well, let's integrate. So f is the integral of f sub x dx. So that's the integral of the first slot. That's y cubed plus 4c xz cubed dx. And if we integrate this with respect to x, what do we get? Well, we get x y cubed, right? Because x is our variable, so y's and x's are like constants. Here there is an x, so we're going to get 2c x squared z cubed. And then one other thing that's going to happen, because we're integrating with respect to x, anything that's a constant with respect to x is going to be completely missed. So that says anything which is a function just of y and z, that's going to be there as well. Okay, we're going to do this 2 more times. So don't worry, if you missed it the first time, you get 2 more chances to see what's going on. Okay, so here we go. Round 2. Here, that's supposed to be our f sub y. So we say, perfect. Let's use that to find f. Integral of f sub y dy. So that's the integral. And don't know why they wrote it this way. I'm going to distribute that through. So I'm going to write this as bxy squared plus 3cy squared z squared dy. When we integrate this with respect to y, well, here we'll get 1/3 xy cubed. And then here we're going to get a c y cubed z squared plus, again, anything which is constant with respect to y. So anything that depends on only x and z. All right. So that might be, for instance, why you notice there's no x cubed z cubed showing up here. Well, that's intentional because it wouldn't be shown. All right. One last slot for us to put in. Okay, so our last one, that's fz. So f should be the integral fz dz. So that's the integral of 2zy cubed plus 6cx squared z squared dz. Well, integral of the first slot with respect to z, z squared y cubed. And now, integral of the second slot, there's a z squared, so that's going to become z cubed divided by 3. So that's 2c x squared z cubed plus anything which doesn't depend on our z. So something which depends only on x and y. So this are 3 ways to look at our function. We need consistency. So we look at our pieces. We say, well, I see what? Oh, you know what I see? I see I forgot to write something down. So what did I forget? Notice I forgot my b here. Sorry about that. Did I forget anything else? Okay, yeah. Sorry. So excited. Okay, so here we go. The xy cubed has to match the xy cubed. So anything which has the same functions has to match. Now, what does that say? Well, from this part, we say, oh, the coefficients have to match, and so we get that b over 3 equals 1, or b needs to equal 3. Okay, good. Now, what else? Well, this 2c x squared z cubed has to match with 2c x squared z cubed, which is automatic, nothing learned from there. All right, no worries. And then we get this c y cubed z squared has to match this z squared y cubed. So these coefficients have to match. And so we say, oh, if those coefficients have to match, then it must be the case that we get that c equals 1. And now, as long as all these pieces here are matching, now we have our potential function. And so we say, okay, so that's our answer. B equals 3, C equals 1, and life is good. Strategy number 1. Okay, great. Wow, that was actually a lot quicker than I thought. Okay, but don't worry. We still have chances for fun, because now we get to do strategy number 2. Okay, here we go. Strategy number 2. And what's going to happen? Well, we're going to say, let's find the curl of f. So we're going to find curl of f, and that's equal to del cross f. All right, so we're saying that's equal to our I, J, K. You got to give yourself some room because you got to write these functions in. Partial x, partial y, partial z. That's our del. And now f, y cubed plus 4cx z cubed. Here, I'll distribute the y through. So that's bxy squared plus 3c y squared z squared. And finally, 2zy cubed plus 6cx squared z squared. All right. Okay. Do your diagonals. I, partial y of this expression. There's only one piece here, right? So what do we get? Well, we get 6zy squared. I. It's the only place where y shows up. J, partial z of this expression. Well, there's only one place where z shows up. So that's going to be, derivative of that is 12cxz squared. All right, and that's J. K, partial x of this expression. Well, there's only one place x shows up, right there. So plus by squared times k. There's no other x terms. Okay, subtract. Now we've got to go the other direction. Okay, so we're taking k, partial y of this term. So here, that goes away. There's no y. That's a 3y squared. So we're going to subtract 3y squared k. Now our other diagonal, well, that's a I partial z. Well, there's only one z, so that gives us what? That's our 6c y squared z. I, but subtract that. And now our last one is partial x times this expression, of this expression, I should say, in j. Well, no x there. Here we'll get 12cxz squared. And so minus 12cxz squared. Minus because of the diagonal going up. And if we group this, what do we get? Well, in the first slot, well, we have 6zy squared common. And now, what's not common? Well, we grabbed everything from here. And here, we didn't grab the minus or the c. comma, 12cxz squared minus 12cxz squared, 0, comma. Here, we can factor out the y squared. What's left? b minus 3. Now, this has to equal 0. And we say, oh, well, the only way for this to equal 0 is we need this part to be 0, and we need this part to be 0, which gives us c equals 1, b equals 3, and lo and behold, the same answer. Huh, life is beautiful, consistent. Oh, yay, us. Good job, us. All right, there we go. 2 strategies. Pick whichever one you're comfortable with. You don't have to do both. All right, let's keep going. Number 5. Evaluate the integral along C. So this tells us we're on a curve. Y cosine 4/3 z ds, where C is the portion of the circular helix given by x equals cosine 4t, y equals sine of 4t, z equals 3t, and t goes from 0 to pi over 8. Okay, interesting. This will be fun. All right, well, let's think about how we can answer this. Well, what are we going to do? What we're going to do is we're starting with our integral, and we're going to use the parameterization to put everything in terms of t. That's the goal. So everything goes to be in terms of t. So we say, okay, some of these things are going to be very straightforward, and some will take just a little bit of work. So when we work for the integral along C, to make it in terms of t, we're going to say, make it the bounds of t. So we have 0 to pi over 8. The y, well, what do we have for y? That's sine of 4t. So we say, okay, cool, we put that in, sine of 4t. So now, that's our y. Our cosine, 4/3, and then our z is 3t. And then our ds. Well, let's pause and bring it out to the side. That's going to be the square root of our x prime of t squared plus our y prime of t squared plus our z prime of t squared dt. Okay, so we got to do some computations. Derivative of cosine of 4t. Well, that's going to be minus 4 sine of 4t squared. Derivative of sine of 4t is plus 4 cosine of 4t squared. And now derivative of 3t is 3 squared. Okay, well, that's going to be what? Square root of 16 sine squared of 4t plus 16 cosine squared of 4t plus 9. And you say, ooh, look at this part. You can pull the 16 out and get sine squared plus cosine squared, which makes it 1. So this part really becomes 16. 16 plus 9, well, that's 25. But another way to say 25 is 5. So we have that our ds is 5 dt. Okay, cool. And now we're like, excellent. Or we could say, excellent. All right, well, we'll clean up just ever so slightly. And that is to say, we can put the 5, we'll put that in the front. We have a sine of 4t, a cosine of 4t, and a dt. Now, there's a couple of ways to solve this integral. Do whatever you're comfortable with. And so, for example, you could say, hey, this kind of feels like double angle formula for sine. Great, run with that. Or you could say, hey, this kind of looks like if you take derivative of sine, it looks like a cosine. Cool, you can run with that. Or vice versa. Hey, it looks like if you take derivative of cosine, it kind of looks like negative sine. Yes, all these are great ways to do it. It just depends how you're feeling. you should pick something that you feel good about. Now, for me, looking at this, I say, you know what? I'm going to set u equals sine 4t. Let's see where that takes us. And, okay, so we're going to do a u substitution. U equals sine of 4t. Then du, well, that'll be 4 cosine 4t dt. Now, the good news is we do have a cosine 4t dt, not a 4, but using advanced marker technology, we can move it across. So 1/4 du is cosine of 4t dt. Nice. All right. So continuing to update, what do we get? Well, plug in the new bounds. Plug in 0. We get sine of 0. 0. Plug in pi eighths. 4 times pi eighths is pi halves. Sine of pi halves? 1. Nice. Then we get 5. And this sine of 4t becomes u. And this cosine 4t dt becomes du times 1/4. Or, this is, when we integrate, 5/4 times 1/2 u squared from 0 to 1. If you plug in 0, you get 0. If you plug in 1, you get 5/4 times 1/2, which gives us our final answer of 5/8. And there we go. All right, that's wonderful. Wonderful. And so that's a line integral, right? Put everything in terms of t and go for it. Life is good. Life is wonderful. All right, let's keep moving along. Number 6, find the work done by the vector field. And so when it's a work, this vector field isn't just any vector field, it's a force field. Ooh, a force field. Oh. Okay, so we have our force field, xz, xy, y minus z. Along the straight line from the point 2, 2, 2, 2, 2, 2, yep, I said that 3 times, to the point 4, 5, 3. All right, cool beans, cool beans. Now, we could have gone lucky, and maybe what we have is something which is a conservative force field. And you can look at it for a minute, and then you realize this is not a conservative force field. I mean, there's a couple of ways you can check, but essentially, like for example here, if you integrate this with respect to x, that would say you should have a 1/2 x squared z, and then if you took the derivative of that with respect to z, you should have a 1/2 x squared in there, and you do not. So it's not conservative. Now, what does that tell us? It means you have to be really careful. It matters how you move between the points. So this is going to become a line integral. But the good news is it's a slightly different line integral when we're doing force. Now we do know it's a straight line. So what do we have to do? Well, we have to figure out what's a way to go from our initial point to the point 4, 5, 3. And it turns out that there's this really great way to parameterize a line segment. So that's going to give us a lot well, I shouldn't say it's going to give us, it's going to make it a relatively straightforward process. So here's the idea. We're going to do the following, figure out what's the vector from these 2 points. So the vector from start to finish. It's like a direction vector, if you will. Well, it is, take the differences. 4 minus 2, 2. 5 minus 2, 3. 3 minus 2, 1. So that's the vector from the start to the finish. And now, this is what you do. We're going to do a parameterization, much like we were doing near the first part of the course. So we're going to have our x, y, z. And first thing is, we write down the start point, 2, 2, 2. All right, so this is the start point. And now we take our direction vector. This is 2t, 3t, and 1t. All right, so this 2, 3, 1, that is this vector there. And finally, here's the beautiful thing. For 0 less than or equal to t less than or equal to 1. Check it out. It's going to work. When you plug in 0, that goes away. You're at your start point. When you plug in 1, you take your start point plus your change from start to finish. You end up at 4, 5, 3. So you're at your end. And that's the way you do it, right? I don't want to call it a trick because it's not a trick. It's a very simple procedure. Start point plus vector that marks the change from start to finish, t. And now you've got your parameterization. Really beautiful because you've got beautiful numbers for t. Life is good. We're not going to compute a ds because that's not the type of integral we have. What is the type of integral we're going to have? Well, for work, we do the following. So work is the integral along the curve of f dot dr. And you might say, oh, okay, what's that? Well, what we're going to do, the dr, you should think of that in the following way. That's your x prime of t, your y prime of t, your z prime of t, and throw in a dt at the end. All right, that's how you should think of dr. It's how you're changing in the x, y, and z direction. And so you say, oh, well, that's going to be pretty clean. So for us, it is going to look really familiar. It's this 2, 3, 1, right? Derivative of x with respect to t is 2. Derivative of y with respect to t is 3. Derivative of z with respect to t is 1. So it's 2, 3, 1 dt. All right. So you're like, all right. So this looks like the integral along the curve. And I'm going to go ahead and write some stuff down. We have our 0 less than or equal to t less than or equal to 1. Maybe we'll save that for the next step. Okay, let's first talk about f. What do we have? Well, we have xz. So what we do is we take x, 2 plus 2t, times z, 2 plus t. All right, so I'm going to make some notes underneath here. Our x, z, comma. Now we have our xy. So x is 2 plus 2t, and y is 2 plus 3t. Okay, there's our x, y. And then comma, y, 2 plus 3t, minus 2 plus t. So that's our y minus z. Okay, so I'm putting everything here in terms of t. That's the goal. Everything gets to become in terms of t. 2, 3, 1 dt. And now the curve, we're going to parameterize that. That's really 0 less than or equal to t less than or equal to 1. Okay, well, we have all the pieces in place. I think, though, I may have misjudged the amount of space it's going to take me to multiply this all out. I do that sometimes. So, but let's go for it. Let's see what happens. 0 to 1. So we're going to have the 2 times this expression. So let's multiply. We have 2 times 2, which is 4. And then we have, so that this 2 here comes from there. 4, 2t plus 4t, 6t, and then 2t squared. Okay? So just 4, 2t plus 4t, and then 2t squared. And then plus 3. Now we're going to do 3 times this part. Well, that's 4. And then we have 6t plus 4t. That's 10t plus 6t squared. Good. Plus 1. And then here, well, the 2's cancel. And 3t minus t is 2t. All right, so we're just putting everything in terms of t. Now we go and start doing our hunter-gatherer phase, right? Integral 0 to 1. Well, for constants, we have 8 plus 12. That gives us 20. And then, what do we have? We have 12t, 30t, 2t. So 12 plus 30 plus 2 makes 44t. All right? 12 plus 30 plus 2, 44. And now we have our 2t squared and our 18t squared. And 4 plus 18 makes 22t squared. And we're like, yes, this is an integral we can do. Calc 1 stuff. Yeah, really it is. We need the Calc 3 to set it up, but really the computations are Calc 1 type computations. So the integral of 20 is 20t. Integral of 44t, 44 divided by 2 makes 22t squared. And then integral of 22t squared is 22 thirds t cubed. And we evaluate from 0 to 1. Well, the good news is you plug in 0, you get 0. So you plug in 1, you get 20 plus 22 plus 22 over 3. And that's our answer, but we're going to go ahead. We're going to put it all together, nice and neat, in a beautiful little package. So that's 60 over 3 plus 66 over 3 plus 22 over 3. And if we add these together, we get 88 plus 60 makes it 148 divided by 3. And that's the answer. 148 thirds. Woohoo! Yeah! So mostly, this is not bad if you just think about what's going on. Get the parameterization. Straight line segments are really clean. Start plus the difference t. Put everything in terms of t. And then you say, okay, now that everything's in terms of t, carry out the integral. Life is good. Bob's your uncle. What a wonderful day in the neighborhood. Great. Let's keep going. Number 7. Evaluate. What? What? Oh my gosh. Oh my gosh. What? Okay, hold on. Let's not panic. Let's think about what we have here. So we're doing the integral from 1 to 2 of 2e to the 2t sine of 3t over t to the 4th, 3e to the 2t cosine of 3t over t to the 4th, minus 4e to the 2t sine of 3t over t to the 5th dt. Yeah. How does this fit into Calc 3? How do we even approach this? So we're going to go through it and talk about this, but we're going to sort of do it in sort of 2 iterations. One is we're going to sort of think about this almost like a Calc 1 problem, and then we're going to rephrase and say, oh, here's sort of the Calc 3 idea that's being hidden here. So as you look at this, you say, I have 3 pieces, but they're kind of tied together. Like some things seem really close to other things. So for instance, here I notice I have a t to the 4th in these 2 pieces, but here I have a t to the 5th. Curious. I also see I have 2 places where I have a sine, right? The sine and the sine. And there's this one place which has a cosine. Okay. And, but then I also have a third thing, which is I have these e to the 2t's. Okay, so it's like I have 3 pieces coming together. And so we start thinking about what's going on here. Because you'll notice here, these terms are sines, well, that's a cosine. These are t to the 4th, that's a t to the 5th, but everything seems to have an e to the t. Well, is there anything else that we haven't really marked up yet, right? Well, we haven't marked up the numbers, so that might give us a clue. 2, 3, 4. Let's start with the trig functions. here I have sines of 3t. Here I have a cosine 3t. Think of a calculus thing. What's a calculus thing that relates sines and cosines? Derivatives and integrals. What's the derivative of sine of 3t? It's cosine 3t times 3. Look at your t to the fourth. What do you have? Well, you have a t to the fourth, a t to the fourth, but here you have a t to the fifth. Now, I said t to the fourth. It's really, downstairs, it's t to the negative 4. So it looks like a t to the negative 4, a t to the negative 4. What's the derivative of t to the negative 4? It's negative 4 t to the negative 5. So that, see that minus also fits in. And you're like, whoa, wait a second. Does that also work with e to the 2t? Well, you have an e to the 2t, e to the 2t. What's the derivative of e to the 2t? It's e to the 2t times 2. So what's happened here? Well, what's happened here is that you could write this in the following way. So this is the integral 1 to 2. It's the derivative of e to the 2t times sine of 3t times 1 over t to the fourth. All right, that's the first slot. Now the second slot, that's e to the 2t times the derivative of sine of 3t times 1 over t to the fourth. Right, because the derivative of sine of 3t is 3 cosine 3t. And this last slot, well, that's e to the 2t sine of 3t times the derivative of 1 over t to the fourth, dt. And you're like, wait a second, what do you have going on here? This feels familiar. It feels like a product rule. So this is a product rule for 3 functions. And like, what? So that says, hey, what do you really have here? You have the integral 1 to 2, the derivative of these 3 pieces multiplying together. Because remember, how does the product rule for functions work? Well, what it says is everybody gets a turn. So you take the derivative of the first, leave the rest alone. Take the derivative of the second, leave the rest alone. Take the derivative of the third, leave the rest alone. And now you're like, oh, well, what does this become? Fundamental theorem of calculus says, hey, this is what? It's the derivative of a function, then you integrate, it's the function. So e to the 2t, whoops, not zt, 2, e to the 2t, sine of 3t, 1 over t to the fourth, evaluate 2 to 1, which gives us our answer. So we plug in 2. We get e to the fourth times sine of 6 times 1 over 16. Then we're going to subtract e squared sine of 3 times 1 over 1 to the fourth. And that's the answer. All right, so that's our Calc 1 setting. Now, but we say, well, hold on. I thought this was supposed to be a multivariable calculus thing. And so how does this tie in? Well, what we can do is we can think, well, maybe this is supposed to be representing something. So what's a something that we have available to us? Well, what we can do is we can sort of reverse engineer. Once we understand what's going on, we could say, oh, what if we're trying to integrate along a curve of f dot dr? You say, okay, well, what's the curve? And what's the f? And, but actually, let's make it really easy. There's a special case when the integral along the curve of f dot dr is clean, and that's the integral along the curve of gradient of f dot dr. Because what does that say? Well, now it's a conservative function. Conservative line integrals are easy. This is equal to what's the value of the function at the end, subtract the value of the function at the start. And say, okay, well, that's cool. So we start thinking, what's a good candidate? And here's the thing. This is embedding in a very particular f and a very particular curve. So the function f that we're going to work with, we're going to call it x, y, z. Right? That's a pretty clean curve. Pretty clean function, excuse me. What's the curve? Well, what we're going to do is we're going to have the following. We're going to have x, that's going to be our e to the 2t, our y, that'll become our sine of 3t, and our z, that's going to become our 1 over t to the 4th, and that's going to be for t from 1 to 2. So let's figure out what happens. Now, where did this come from? This x, y, z? Well, it's like we're multiplying the three pieces together. So that's sort of our motivation for it. And in some sense, this is showing you, hey, product rule can come from our multivariable setting, and relatively straightforward. Okay, so let's check what's happening here. Gradient of f, well, that's our yz, comma, xz, comma, xy. And so what do we get? Well, this becomes the integral along the curve of, well, so we're going to put everything in terms of t eventually, but we have integral along the curve of yz, xz, xy. And what is our dr? Well, our dr is our x prime, y prime, z prime, dt. And now we say, oh, so this says if you integrate along the curve of x prime yz plus x y prime z plus x y z prime dt, what do you get? Well, this is equal to x, y, z evaluated from the start to the end. And now that's exactly what's going to happen here. So where is our start? Well, our start would be, you start with this point, and you say plug in 1. So that's e squared, comma, sine of 3, comma 1. What's our end? Our end would be our e to the 4th, sine of 6, and our 1 over 16. And so when you plug this in, you take x, y, z, so that's e to the 4th, sine of 6, 1 over 16, subtract, plug in x, y, z, e squared, sine cubed 1. And then the only other thing to check is that, hey, this part right here, this is the integral we were given. And that's the idea. That's the whole thing. Now, it's, I'll be honest with you. When I first saw this, I was like, what? And then I saw it and I was like, huh? And I had to think about this for a while. It's one of those things that once you see it, you're like, oh, okay. But I personally, if I saw this out in the wild, and, you know, I'm a little ashamed to admit this. If I saw this integral walking down the street, I might cross the street to the other side. I'm sorry. I know I shouldn't do that, but you know, some integrals just don't look pleasant. And this is one of those. But once you see it, like, oh, wasn't that clever? But I don't like having to become clever on the spot. But that's my own opinion. So, but anyways, how would you approach the problem here? It's sort of like the thought process was very similar to what I started with, right? Say, hey, gosh, I have three terms. How can I connect them together? And you'll see that like, oh, some pieces are close, and then other pieces are kind of close-ish, but look almost more like a derivative. And then, oh, that starts building things up. And once you understand that, then it all comes together. But all right, well, that's enough fun with this one. Let's keep going. All right, number 8. Evaluate the integral. So we're going from 111 to 333. Okay, so it says we're starting at a point, ending at a point, but pause for a second. Notice what it doesn't say, because what it doesn't say is almost as important as what it does say. It doesn't say how we're getting between the 2 points. What? Now that's going to become important here. Okay, so we're going from one point to another point. And we have 6x to the 5th y squared z cubed dx plus 4 minus 2x to the 6y cubed z cubed dy and minus 3x to 6y squared z to the 4th dz. Now, notice we're supposed to evaluate the integral. And we're only given where we start and where we end. If we're not told the curve and we're just told the endpoints, what must be true? It must be conservative. Okay, so our sort of like strategy number 1. So for this to be answered, right, if there is an answer, then what must be true? Then this must be conservative. And this is actually going to really drive both strategies. And so, okay, so it's conservative. Find the potential. Yes, there's a potential function. And if we can find it, life is good. Okay, so that's our plan. And in particular, what can we say? Well, what happens is that we can think of this. This is the integral along a curve C of, and I'm just going to group things together, 6x to the 5th y squared z cubed, comma, 4 minus 2x to the 6th over y cubed z cubed, comma, and minus 3x to the 6th over y squared z to the 4th dot dr. So the punchline here is that this thing right here, this has to look like f sub x, f sub y, f sub z, right? It's a potential function. So potential functions means this is the gradient of some function. And now we're like, oh, so we just have to reconstruct f. And if we can reconstruct f, then what will happen is that this integral, we'll go ahead and write down what happens. This becomes equal to f evaluated from the start to the end. So it's f. We know the start is 111. We know the end is 333. So this becomes f of 333 minus f of 111. So if we can find f, we win. So we got to find f. But that's okay. We know how to find f. Because we have the partial derivatives, we're going to build up what f must look like. Okay, well, let's begin. We'll start with the first slot, that's f sub x. So we say, well, f should look like the integral of f sub x dx. Well, that's the integral, 6x to the 5th over y squared z cubed dx. And if we integrate that, we get what? X to the 6th. The y squared z cubed is a constant. Y squared z cubed plus, well, a function which doesn't depend on x, right? So what doesn't depend on x? It's a function of y and z. All right, good, good. So it's a constant with respect to x. Now we do the same thing with the other slots. So f, the integral, f sub y dy. Okay, so that's the integral of 4 minus 2x to the 6 over y cubed z cubed dy, which is what? Well, the integral of the first term, 4y. Integral of the second term, well, here you have essentially y to the negative 3. You add 1 to the exponent negative 3, and you divide by that new exponent negative 2. You'll end up with x to the 6, y squared z cubed, plus anything which depends on things which are not y. So some constant xz. And then our last approach, we'll integrate fz dz. Okay, that's the integral of minus 3x to the 6 over y squared z to the 4th. And if you integrate here, that's like z to the minus 4, add 1, z to the minus 3, divide by minus 3, and what do we end up with? We end up with x to the 6 over y squared z cubed plus something which doesn't depend on z. So that's something that's a constant x comma y. All right, so we are now ready to say, let's look at our pieces. Well, you need to get consistency. So anything with multiple variables has to be consistent. Now, the good news is they all have x to the 6 y squared z cubed. Cool. And then you say, okay, plus any other pieces. So pieces which only depend on a single variable, because those will only show up in one place. So there's a 4y. So now we say, great, we can put that together and say, we can use our function f will look like x to the 6 over y squared z cubed plus 4y. Now, that is a potential function. There's actually infinitely many potential functions. Can you see what you do to this one? You add c. That's right. Add in any c that you want. And but what are we going to do? We're going to add 0 and say, okay, there's our potential. So we're now ready to answer the question. So here we go. We plug in 3, 3, 3. So we're going to get 3 to the 6 over 3 squared, 3 cubed, and plus 4 times 3. All right, whatever that turns out to be. Subtract, plug in 1. 1 to the 6, 1 squared, 1 cubed, plus 4 times 1. And if we do that, well, here we get 3 squared, 3 cubed, that's 3 to the 5th. 3 to the 6th divided by 3 to the 5th is 3. 3 plus 12 is 15. Subtract 1 plus 4 is 5. That gives us a final answer of 10. And so the answer is 10. Good, good. Now, that was strategy number 1. But we don't call something strategy number 1 unless there's a strategy number 2. And here's strategy number 2. It's to say, well, you know what? I can, because it's conservative, I get to pick the curve. So let's pick the curve. So here's a really clean curve. So we're going to let x equals t, y equals t, z equals t, and we're going to let 1 less than or equal to t less than or equal to 3. Where do you start at time 1? Start at 1, 1, 1. Where do you end at time 3? You go to 3, 3, 3. So if we choose this, then our integral becomes what? 1 to 3. All right, we're putting everything in terms of t. We get 6 t to the 5th over t squared t cubed times 1. Right, that's the derivative of x is 1, plus 4 minus 2 times t to the 6 over t cubed times t cubed. Right? I'm just plugging in x equals t, y equals t, z equals t. And dy is 1 minus 3 times t to the 6, because x is t, over t squared t to the 4th, and dz is 1. And all of that becomes dt. Well, this is the integral 1 to 3 of, well, all the t's cancel here, so that's 6 plus 4. Here all the t's cancel, minus 2. Here all the t's cancel, minus 3. Well, that's the integral of 5 dt from 1 to 3. That's 5t, evaluate from 1 to 3, which makes this 15 minus 5, also known as 10. And they're both valid answers. And you look at this and say, I kind of like this one. Great! Great! If you love it, run with it. If you don't, this is also perfectly fine. So here, this is strategy number 2. And I should have mentioned what this strategy is. I like to call this BYOC. Bring your own curve. Right? We have to start at 1, 1, 1, end at 3, 3, 3. We know it's conservative, otherwise it would be a pointless question. So we bring a curve that's very simple to describe and gets the job done. And that's the answer. Nice, nice, nice. All right, good. Well, let's keep going. Number 9. Evaluate the line integral. So it's a line integral, x squared plus yz ds, where c is traced by r of t is t, 5 minus 4t, 8t, and t goes 0 to 1. All right, simple strategy. We're going to put everything in terms of t. And this feels like ones we've already done, so hopefully we'll get really good at it, right? So we have our x, our y, and our z. Okay, so I should make my z look like a z. And what do we do? Well, let's go ahead and do some ds computation here. So ds, that's the square root of x prime squared plus y prime squared plus z prime squared dt. So for us, that becomes the square root of 1 squared plus negative 4 squared plus 8 squared. And so that's 1 plus 16 plus 64. Oh, that's actually a nice number. That's 81. And square root of 81 is 9. Okay, so we're now ready. We've done the prep work. So to begin, we say, hey, this integral along the curve of x squared plus yz ds, the way we do it is we put everything in terms of t. So our bounds, 0 to 1. Our x is t. So this becomes t squared and plus y, 5 minus 4t times z, 8t. And ds is 9t. And there we go, right? So just recapping here, x squared, and here you get y, z. And this is our ds, and I put 9t, whoops, and I shouldn't have put 9t, I should have put 9 dt. There we go, sorry about that. That's okay, that's why we have times to check our work and make sure we correct our mistakes. Well, let's see, what does this become? Integral 0 to 1 of t squared plus 40t, right? 5 times 8t is 40t, minus 32t squared. Interesting choices here. And then there's a 9. All right. And, well, that becomes integral 0 to 1 of 40t minus 31t squared, right? Because t squared minus 32t squared times 9. Or that is integral 0 to 1, 360t. 40 times 9 is 360. And minus 279t squared. 9 times 31, 279 dt. Well, now we integrate. Integral of 360t, that's going to be 180t squared. Right? Because you add 1, divide by 2. 360 divided by 2 is 180. And here, well, it's going to be a t cubed. 279 divided by t cubed is 93. And we're going to evaluate this, 0 to 1. So this becomes 180. Subtract 93 and subtract 0. And okay, 180 subtract 93 is a number. No, we don't have to do that. We know what number it is. It's 87, right? And there you go. Oh, nice. You know, these are really clean sometimes when you have a very, very simple curve, right? This is a straight line segment. Nothing bizarre. No like bending things. Life is good. This is the kind of curve that we like to integrate along because it becomes a very straightforward integral in t, and we're just like enthusiastic thumbs up for that. Nice. Okay, well, we're almost done. Let's finish it. Let's do it. Yeah! Number 10. We're asked to evaluate this line integral. Integral along a curve 3x plus y, x plus 3y ds, where the curve is part of the circle x squared plus y squared equals 4 in the first quadrant going from 0, 2 to 2, 0. Okay, let's start by understanding our curve. This is going to be interesting. Well, we should sketch it, and so we're in the first quadrant, so that'll simplify things a little bit, at least in terms of understanding the picture. 0, 2 says that we're going to start up here. So this is our start. And 2, 0 says that we're going to end down here. So start at 0, 2, end is at 2, 0, and we're on the circle. X squared plus y squared equals 4. So it's the circle radius 2, centered at the origin. So we're moving in that direction. All right. Well, what do we need to do? Well, because of the format here, we've got to find a parameterization. And they didn't give us one. So that means it's sort of dealer's choice. And you might say, well, what's a parameterization? You can, for instance, say, oh, hey, I have an idea. I could solve for y. If you do that, subtract and then take a square root. You get y equals square root of 4 minus x squared. So here's one parameterization. I'll call it C1. We could say, we can do let x equal t and y equals the square root of 4 minus t squared for 0 less than or equal to t less than or equal to 2. And so that's a very, if you think of y as a function of x. However, it may not be the simplest parameterization. And remember our goal. We love ourselves a lot, right? We want the best for ourselves. We're like, come on, you are worth it. Oh, thank you, man. I really needed that today. And so, what are we going to do? Well, we're going to say, can we make our lives simple? We start saying, okay, how can we do that? What do we see? What do we see? We start saying, circle. Now, we're like, wait a second, we're like really good with the parameterizations for circles. Because if you think back to trigonometry, those were good days. There's actually a really cool parameterization for circles, which is you said, you would set cosine t, sine t. And that traces out a unit circle. Now, two issues. This is a unit circle. This is not a unit circle. It's a circle radius 2. That is easy to fix. So if you do 2 cosine t, 2 sine t, so right, this gets you on a circle of radius 2. And you say, all right, great, loving it, cool. But now there's another issue. The other issue is orientation. Direction matters. Change the orientation, you change the sign. Now, you could just say, I'll go with the current orientation and throw a minus sign in. But we're going to do something, which is we're just going to have it go the other way. We're going to be a little bit sneaky. And not terribly sneaky, but now, here's the thing. If you just do the following, 2 sine t, 2 cosine t, you say, if you're on the circle of radius 2, what happens? Well, you start not here, you start there, and then you go in the right direction. So at time t equals 0, you're at the right starting point, 0, 2, and at time t equals pi halves, you're at the right ending point, 2, 0. So you can do a couple of modifications. So our curve 2, we can say, let's let 2 sine t, 2 cosine t for 0 less than or equal to t less than or equal to pi halves. And now let's do curve 2. And if we have energy, then we'll try curve 1. All right, so we begin curve 2. And I like to think this is simpler. Why? Because there's no square root. Okay, if you have a choice for a circle, try to do sines and cosines. It's the most elegant way to work with circles. All right, remember that. If you have a circle, sines and cosines. So, here we go. We're going to replace everything in terms of our parameterization. So we have our integral along C of 3x plus y, x plus 3y ds. We have our x and our y. We'll do a quick computation here, ds, square root of, and now take the derivative of x prime squared plus y prime squared dt. Well, that's the square root of, derivative of 2 sine t, 2 cosine t squared, and derivative of 2 cosine t is minus 2 sine t squared. And, okay, so this becomes square root of 4 cosine squared t plus 4 sine squared t. And you're like, oh, come on, Steve. You see what's happening. Yeah. Pull out a 4, cosine squared plus sine squared, and that's 1. So this becomes square root of 4. Or, really, 2. That is nice. We approve. Okay, so with that in place, here we go. We get, this is equal to the integral. We're going to go 0 to pi over 2, right, because those are our t-bounds, right, 0 to pi over 2. And now x, well, that's going to become 2 sine t. So that becomes 6 sine t plus 2 cosine t times 2 sine t plus 6 cosine t. And then the ds is 2 dt. All right. Well, we start distributing. And we're going to FOIL. So we get this is equal to integral 0 to pi halves, 6 sine t, 2 sine t, that's 12 sine squared t, plus 36 sine t cosine t, plus 4. All right, now we're doing our inner ones. Sine t cosine t, plus 12 cosine squared t, and all of that times the 2 dt. Okay, so good news here. What can we do? This 12 sine squared plus the 12 cosine squared becomes 12. And don't forget, add in the 2 as well. So if we take 12 times 2, we get that this is 24. All right. And now we have the rest of it. And for the rest of it, what do we get? Well, 36 plus 4. And don't forget the 2 again. Now, 36 plus 4 makes 40 times 2 gives us 80. Okay, so now we have 80 sine t cosine t. All right. Now, what can we do? Well, we can make this work to our advantage, right? Because here we can use the fact that 2 sine t cosine t is equal to sine of 2t. So note, 2 sine t cosine t equals sine of 2t. That allows us to rewrite this again. So this becomes integral 0 to pi over 2 of 24. And then we're going to think of this as 40 times 2 sine t cosine t. So plus 40 sine of 2t. All right, dt. And we integrate that. We're in the home stretch. That's 24t plus, well, integral of sine is minus cosine. So minus cosine 2t. And now divide by 2. So that's a 20. And we're going to evaluate 0 to pi halves. And what do we get? Well, 24 times pi halves, that's equal to 12 pi. Cosine of pi, well, that's minus 1. Minus minus makes plus 20. So that's when we plug in pi halves, subtract, plug in 0. 24 times 0 is 0. And then cosine of 0 is 1. So 0 minus 20. And now we say, so that really becomes a plus 20 plus 20 more. So we end up with 12 pi plus 40. And there we go. That's the answer. We're done. We're done. Oh, well, that's if we use curve 2. What'll happen if we use curve 1? Before we start, do we know the answer? Yes, it's got to be 12 pi plus 40. It has to be. Has to be. Because there's consistency. It doesn't matter which curve you travel. That's not right. It doesn't matter the parameterization for the curve you travel. That's what I meant to say. Different curves can produce different results. Different parameterizations will produce the same result. However, the journey can be different. So let me grab a piece of paper. I have some spare paper here. Don't worry, I have lots of paper. Grows on trees. So here we go. A nice fresh sheet. We're going to cover up all that beautiful work we did for curve 2. And hopefully we're going to do it and get a very similar answer. So, where do we begin? Well, let's remind ourselves what we're doing. We're going to find the integral along C of 3x plus y times x plus 3y ds. Okay. Well, for that, we're using our parameterization, so we have our x and y. So we note that x equals t, y equals the square root of 4 minus t squared, and ds, well, that's going to be the square root of x prime squared plus y prime squared dt. So let's work on our ds for a few moments here. So that's the square root of, well, the derivative of t is 1. You're like, Steve, this is easier. We should have started with this. And then we're like, the derivative of y, which is something I'm not very excited to take the derivative of, right? But we got to do it, right? So you should think of this as 4 minus t squared to the half. So the half comes down. 4 minus t squared to the minus a half. And then times the derivative of the inside, which is minus 2t. And then we're going to square that, dt. Well, some good news, the 2's cancel. The minus, when we square it, that goes away. So this becomes the square root of 1 plus, here, we'll get t squared in the numerator, and downstairs, because we're squaring it, the minus squared goes away, t squared. 4 minus t squared to the minus 1/2 becomes a 4 minus t squared downstairs. Okay, so that's good. Well, common denominator would be 4 minus t squared. So this becomes the square root of 4 minus t squared plus t squared over 4 minus t squared dt, which upstairs you get t squareds canceling. And so we'll mark that. We'll go ahead and remark this a different color. T squared. And square root of 4 is 2. So we get 2 over square root 4 minus t squared and dt. All right. So now we're ready to put everything in terms of t. Our parameterization goes from 0 to 2. So our time, 0 to 2. And we get 3t plus square root 4 minus t squared times t plus 3 square root 4 minus t squared times 2 over square root 4 minus t squared dt. So we expand. This becomes integral 0 to 2. We have 3t squared plus 9t square root 4 minus t squared plus t square root of 4 minus t squared plus 3 times 4 minus t squared. All of this gets multiplied by 2 over square root of 4 minus t squared dt. Okay, nice. We're making progress. We can start gathering things together. So this becomes integral 0 to 2. We can say, oh, check this out. This is cool. Notice here, that's 12 minus 3t squared. That's a 3t squared. That's a 3t squared. So those cancel. So what do we really have? We have 12. Cool. And then these two terms combine plus 10 times t times square root of 4 minus t squared. Okay. And, right. Good. And all of that is going to be multiplied that by 2 over square root 4 minus t squared. Okay. Well, what does this become? This becomes, we distribute through, 0 to 2. We have 12 times 2 square root of 4 minus 2 squared. So that's 24 over the square root 4 minus t squared plus, okay, here we distribute. Notice what happens. The square root of 4 minus t squareds cancel. So we get 10t times 2, and that's 20t. Okay, nice. All right. Now, one of these will be a very easy integral. Can you guess which one? Oh, no, you know, you don't have to guess. The integral of 20t is going to be very straightforward. So that becomes, we integrate that, that's our 10t squared. Okay. Plus, now we got to do this other one. And let's go ahead. We're going to work this out. We're going to do this. We're going to do this. So let's suppose we were asked to integrate 24 over the square root of 4 minus t squared. Okay, we got to think about what this becomes. And, all right. Sorry, I'm not trying to be pensive on purpose. I'm just making sure we're doing well. Because I think we deserve to do well. We're putting a lot of work into this. And so we want to make sure we get the right answer. Well, this is a trig sub. We do t equals 2 sine theta. Then what does dt become? Well, it becomes 2 cosine theta d theta. And if you carefully start digging through this, what do you get? You get 24. 4 minus 4 sine squared, that becomes 4 times 1 minus sine squared, which becomes cosine squared. Take the square root, you get 2 cosine theta. dt is 2 cosine theta d theta. So you get 2 cosine theta d theta. And then you're like, oh, those cancel. So what are you left with? Well, you're left with the integral of 24 theta. 24 d theta, which becomes 24 theta. You say, but wait, what's theta? Well, theta, you can solve. Sine of theta is t over 2. So this becomes 24 times arc sine of t over 2. And I forgot to add in a plus c. But that's the indefinite integral. Here we're doing a definite integral. So plus 24 arc sine of t over 2. Walk down memory lane. Back when we cared about arc sine, right? we always cared about arc sine. Come on. All right. Evaluate that from 0 to 2. We're almost there. So when we do this, we plug in 2. 10 times 2 squared is 40, plus 24 arc sine of 1, 2 over 2. Subtract, 10 times 0 squared is 0, and arc sine is 0. I don't have a lot of space, but I'll go ahead and tell you arc sine of 0 is 0. And arc sine of 1, what angle gives you an arc sine of 1? Well, sine of pi halves is 1. 24 times pi halves would be 12 pi. So here we get 40 plus 12 pi. It's the same. The exact same. What? That's amazing. Wow, the crowd goes wild. Oh my gosh. What a world. Surprise? No. But it's nice when things are true. We love it when things are true. So, again, remember, be kind to yourself. You deserve to be kind to yourself. You're a great person. And I'm really thankful that you've been joining me and working through these problems, because there's some wonderful problems that we went through today. So thank you for putting the time and energy in. So that brings us to the end. Keep at it. You're going to get this. You're going to get it. It's practice. And it should have some familiarity, right? It's parameterized curves. It's things that you know how to do. You're going to do great. I believe in you. Thank you for all your work. Thank you for joining me. And maybe we'll get together again, right? I hope so. Okay. Bye.